Hello. Thank you for joining us at the Charge Virtual Conference on EV Engineering. The topic of this session is how to gain flexibility and speed in prototyping and manufacturing EV motors, and it's brought to you by Infinitum Electric. There'll be a Q&A session after the presentation, so click the Q&A button on your screen at any time to submit your questions. And without further ado, please welcome our speaker for this session, Paulo from Infinitum Electric. Welcome.
Hello everyone, I am Paulo Guedes-Pinto, VP of Technology with Infinitum Electric, and today I would like to talk about our innovative AutoFLUX permanent magnet PCB-based electric machines and how they can become a game changer in electric vehicle applications. First, I would like to give a brief introduction to our AutoFLUX PCB Stator machines. This animation shows the main components of our electric machine. The key component of our technology is the PCB stator, which is shown here as the green disc. Our PCB stator replaces the traditional iron core copper wound stator of conventional machines. It is very light and compact. For the same power rating, our stator typically weighs about 1/10 of the weight of a conventional stator. In the absence of a stator core, our motor has two rotor discs that form the magnetic circuit and carry the permanent magnets to generate the main magnetic field that interacts with the rotating field produced by the stator winding, generating the torque that causes the motor to run. Rotors and stator are housed in a cast aluminum enclosure. A second enclosure carries the variable frequency drive that supplies power to the motor and controls its speed. The motor and drive form a compact system that is very light. Typically, our machine weighs less than 50% than a conventional iron core motor. I would like to highlight some of the other advantages of a PCB Stator AutoFLUX machine. As we do not have an iron core, there are no core losses. In addition to that, the magnetic flux produced by the rotor is steady, is not affected by slots in the stator, so there are no eddy current losses in the rotor or the magnets. By not having core losses, the efficiency of the motor is fairly high throughout a wide range of load and speeds. In addition to that, as we do not have an iron core, there are no magnetic forces between rotor and stator, so there are no cogging torque, there are no magnetic noise. The stator itself has a very high surface to volume ratio, so we can actually operate our stator with a much higher current density than a conventional machine, typically 2 to 3 times higher. In addition to that, as I mentioned before, our motor is much lighter than a conventional machine. The motor alone can be 2 to 3 times lighter than an equivalent iron core motor. I would like now to describe how do we design our prototypes. By eliminating the stator iron core, we also eliminate the nonlinearities and hysteresis that are common to the design of conventional electric machines. Infinitum Electric has developed a design program called AutoFLUX, which is optimized for the design of AutoFLUX permanent magnet machines with PCB stator. By providing a series of parameters and ranges for those parameters, the program can generate, in some cases, hundreds of solutions from which the design engineer can pick the best option for a particular application. Typical selection criteria for designs can be best efficiency to weight ratio, minimum active weight material, minimum diameter, or a combination of all of those. Once the design is selected, the engineer can choose to validate that design using finite element analysis. With the help of ANSYS, Infinitum Electric has developed an optimized finite element analysis model that represents our machine topology very accurately. Within hours, we can verify back EMF values calculated by our AutoFLUX tool, and within 2 days, we can validate torque values predicted by our design program. Once the design is validated, we can move on to the next phase, which is basically generating the Gerber files for the stator and drawings for rotors and other parts of the machine. Infinitum Electric motors and drives are designed having reliability in mind. All the critical power electronics components used in our drives have either industrial or automotive grade. Bearings are selected to achieve at least 50,000 hours L10 life. In addition to that, our prototypes are extensively tested in our labs. We have several dynamometers, and we would have motors running at different load conditions and different speeds all the time. In addition to that, we send samples to a third-party lab for accelerated lifetime tests. At any given time, there will be at least one motor undergoing accelerated lifetime tests. After we complete our design, build and test our prototypes, we move our machines into manufacturing. Our machine topology lends itself for very simple manufacturing processes, which we'll be discussing in the next few slides. Our machine topology is very simple and lends itself to simple manufacturing processes that can be easily automated. The rotor itself is simply a steel disc that carries magnet segments. The magnets can be cut from pre-sintered blocks very easily, and after the magnets are cut and plated, they can be bonded to rotor discs very easily using robotic arms, and typically a rotor disc assembly can be produced within 3 minutes. After the magnets are bonded to the rotor discs, they can be magnetized in one single operation, which takes less than 60 seconds. The key component of our machines is the PCB stator, which can be built using standard PCB manufacturing processes and using standard PCB materials such as copper-clad laminates, prepreg fills, and undergoing traditional and standard manufacturing processes such as lamination, drilling, via plating, and application of solder mask. The processes are fundamentally the same processes used to make conventional PCBs for electronics, and a number of vendors have the capability to produce our stators. The mechanical parts of our machines are very simple and use conventional materials. As an example, the motor housing uses cast aluminum, which in small quantities can be produced by sand casting, and in large volume production can be easily converted to die cast. The typical components that we use in our machines have features intended to facilitate assembly and further process automation where needed. The mechanical features I mentioned previously that facilitate the assembly process can also enable process automation. This slide shows a proposed assembly line for our motors and drives. In the first portion of the process, the motor is assembled by three robotic arms. First one installing the first half of the rotor into the housing and dropping the stator. The second robot installs the second rotor disc, and the third one installs the second half of the housing and apply the bolts connecting the two halves. On the second phase of the assembly process, the VFD housing with the VFD already installed inside is dropped on top of the motor. A robotic arm installs the cover to the VFD housing, and at the end the motor is ready for testing and shipping. Infinitum Electric approach to product design and manufacturing takes advantage of the simple geometry of our machines and leverage existing processes used to make other products. As an example, the PCB Stator can be built in any PCB production line anywhere. Most of our mechanical components and electronic components are off-the-shelf parts, or they can be easily produced using conventional processes. As an example, the motor housing or the VFD housing can be made using simple casting processes. The simplicity of our designs lend themselves to easy assembly and also for scaling up production depending on volume. It's easy to transition from manual assembly to semi-automated assembly to fully automated assembly without dramatic capital investments, given the simplicity of our machines. In addition to that, Infinitum Electric can license the manufacturing of components to different contract manufacturers that are better prepared to handle high volume production. I would like now to summarize and highlight some of the key benefits of our motor topology for EV applications. Beginning with having high efficiency, lightweight, being power dense and quiet. Also has a robust design that can be easily verified through testing. It does have a quick design and prototyping cycle compared to a conventional electric machine. And thanks to its simplicity, it has simple and scalable manufacturing processes. If this sounds to you, it is a good solution for EV applications, you probably guessed right. That's all I have for today. I hope this presentation had provided you with some good insights about our technology, how our product is designed and built, and how it could fit into electric vehicle applications. I would now answer to any questions the group might have. Thank you very much for the opportunity. Have a good day.
Thank you for the presentation. Now we'll begin the Q&A session, so please submit your questions by clicking the Q&A button on your screen. I see we have a few questions submitted already. If you could begin by reading the question aloud, that would be great.
Yeah, I will start with the first one. What would you expect to see from your e-machines in terms of efficiency objectives for costs per kilowatt or energy density, torque density, and power density? We are currently working on a 150 kilowatt prototype for traction motor applications. The expectation is this machine should achieve around 10 to 12 kilowatts per kilogram when it's fully finished and refined, which should probably take another 6 to 8 months to get to that level. The initial prototype is being built without having low weight in mind. We just want to prove the technology and test performance. And then the next step would be to convert components into lighter weight components. We don't have a good sense of the cost per kilowatt at this point, as it's in development.
See another question here around today the EV industry is trending towards 800 volts and using silicon carbide MOSFET based inverters. Is your motor suitable to such voltage and high operating frequency? So the answer on both is yes and yes. In terms of the 800 volts, that's actually what we're designing our initial traction motor to. And in terms of silicon carbide, our motor actually takes advantage of that higher frequency, operating frequency, and works well with silicon carbide MOSFETs. With that said, we also have designed inverters utilizing IGBTs, and so we are capable of designing systems with both technologies.
Okay. We have another question here. What is the typical efficiency of these machines? So our designs, as our normal design practice, we shoot for I5 efficiency, which of course varies as a function of machine speed and power. So most of the designs that we're building right now, there are in the range between 5 and 15 horsepower. The motor efficiency varies between 90, 91% all the way up to 93, 94%. And the system efficiency, which combines the motor and drive, typically varies between 89 and 92% efficiency.
To add to that comment, the motors that we're currently in production with are industrial motors, so they haven't been optimized for the efficiencies that would typically be expected in EV applications or for the power density that would be expected in EV applications. So when Paulo mentioned the 10 and 15 horsepower, those are industrial motors. For the work that we're doing for some of the traction applications, the efficiencies are higher. And as Paulo mentioned earlier, in terms of the power density, those two are significantly higher.
We have another question here. What end user context are your motors designed for? For instance, traction motor applications for EV. Yes, we are currently, as I mentioned before, we're working on a prototype, 150 kilowatts prototype continuous power, which is intended for traction motor applications. But we have been looking into designs for auxiliary systems in vehicles. And those designs typically are in the range of 10 kilowatts, 15 kilowatts. So there are a number of different applications where our technology can be applied to.
There's a question around what is the current power density of PCB motors versus conventional motors? So I think Paulo mentioned that we're about 3 times higher power density. So on our traction application, typically we're utilizing oil cooling, and we're seeing a power density in the range of 42 to 56 amps per millimeter squared, whereas a conventional copper wound iron core oil-cooled motor is typically seeing current densities in the range of 8 to 11 amps per millimeter squared. So significantly higher current density there.
We have a question here about what is the maximum temperature rise that can be achieved and what is the maximum voltage rating that can be achieved. So as we mentioned before, most of our designs they target a DC bus voltage, supplying voltage to the inverter in the range of 800 volts. And this seems to be the majority of applications for where the EV industry is moving to. In terms of temperature, our designs currently, they use FR4 in the stator, which is a material typically used in PCBs for a number of different applications. The temperature rating is temperature rise of total absolute temperature of 130 degrees Celsius. What we have seen in our applications with oil cooling, the temperature rise of the stator, even with the higher current densities that Bhavnesh just mentioned, are around 10 to 15 degrees Celsius above coolant temperature. So in cases where the coolant comes into the motor at around 60 degrees Celsius, the absolute temperature that is expected would be around 85 to 90 degrees Celsius.
I see another question here around the rotors. How are the rotors cooled? So our rotors do not have any losses and therefore are not generating heat. Maybe Paulo, you can elaborate a little more on that.
Yes, the nature of our machine, there are no eddy current losses in the rotor, either the rotor structure or the magnets. So the rotor doesn't produce any heating, and the temperature of the rotor is pretty much defined by the temperature of the coolant around it. So in the example that I just mentioned before, the rotor temperature should not exceed 80 to 90 degrees Celsius. So we don't need to use high temperature rated magnets in our designs.
Another question around how many rotor stator pairs can we request for additional power? So it's really almost infinite. Obviously, there would be some limitations in terms of feasibility, but in terms of the ability to stack multiple units, you could theoretically stack as many as you want. For our initial traction motor, we actually are stacking 3 modules, if you will, essentially of 50 kilowatts each to come up with a 150 kilowatt stack. And again, that could vary depending on the application, and the topology of that could also vary.
That's correct. So that this 150 kilowatt prototype that we are building has 3 stators and 4 rotor discs, and the stators and the discs are interleaved. So, we have another question here. What is the power factor range for the design motors? So our power factor, the motor power factor tends to be very high because the dominating portion of the impedance of the motor is the resistance. The inductance is very low. So in our industrial applications, the typical power factor is around 0.9. That's the power factor of the motors, not what is seen by the grid.
There's a question here around how many PCB layers do you have? That varies depending on the application, the amount of current that we're running through that application. Paulo, I don't know if you want to comment any further on that.
Yes, we have designs that vary all the way from 12 layers all the way up to 24 layers. And this is dictated primarily by the power and torque requirements of each application. There is one more question here. How did you reduce eddy current losses within PCB conductors? So the two major electrical loss mechanisms in our machines are I square R losses and eddy current losses in the conductors of the PCB stator. So the way we mitigate eddy current losses, our design tool, AutoFLUX, it can manipulate the width of the traces in the winding to reduce eddy current losses, or we can prioritize eddy current losses over over I square R losses by changing the width of those conductors. So in most of the designs that we have, we try to minimize eddy current losses as much as we can. But in some applications, it may be actually interesting to minimize I square R losses depending on how the machine operates. We can do both.
I see a question here around the 100. You mentioned that your motor is 150 kilowatts continuous. What is the peak power? So Paulo touched on the oil cooling that we have and the fact that the oil cooling is in direct contact with the source of the heat. And so we're able to more efficiently remove that heat from the machine. And ultimately, our peak power will be much higher. The peak to continuous ratio will be much higher. In our initial testing, where we took a traditional air-cooled small motor and applied air cooling, what we saw was we were easily able to take that power 3 times higher than the rated continuous power. And so we expect to see similar results with our 150 kilowatt motor. That's still to be determined after our testing, but all indications are that we'll see some pretty significant ratios of peak to continuous power ratings.
We have one question here that asking, does the design topology require that the torque is compromised for high speeds and compensating for a higher gear ratio? So fundamentally, our motor is a permanent magnet synchronous machine. So it behaves from the power and torque standpoint the same way as a permanent magnet synchronous machine. So typically our design has a region, what we call constant torque, which basically runs all the way from near 0 RPM to the rated speed. And above the rated speed, the motor operates into a constant power mode. In other words, as you increase the speed, the torque will drop, maintaining the power, the constant power. So it's no different than a conventional permanent magnet synchronous motor machine.
Okay, we have about 2 minutes remaining. Any last questions?
Okay, there is a question here if we study circulation currents between coils due to manufacturing errors. So one of the advantages of the PCB stator is that the PCB stator is built in a mostly automated process where there is very little dependence on operator skills. So each layer after the etching process is inspected to an automated optical inspection. So any manufacturing defects are catched at that point and corrected. So by the time the stator is fully laminated, the chances of having defects in the stator are diminished, and of course the stator can be tested like a conventional stator to detect possible manufacturing defects.
All right. Well, thank you, everyone. Feel free to reach back out to us if there's interest in exploring this further or if there's any follow-up questions. Appreciate everybody making time to listen to our presentation. Thank you, Paulo.
Thank you, everyone. Thank you for the questions.
Bhavnesh, Paulo, thanks again for the presentation and for everyone coming to attend. That concludes this session.